This video is the companion to our full-featured article in Astronomy for Change. Link in the comments section below. James Webb Space Telescope Deep Field confirms evolutionary theories of the early universe. Welcome friends, Dr. Jim Daly, your host here, to present some new and remarkable discoveries that have been realized with the public release of James Webb Space Telescope data and imagery. We knew that JWST would answer many questions while posing new ones, that it would dispel some myths and uncover some mysteries while creating new ones. But to confirm a line of reasoning about the early universe right out of the gate was unexpected. What am I talking about? On July 12th, NASA, along with representatives of the European and Canadian space agencies, partners in the mission, unveiled the results of 5 separate studies, images and data with a high wow value. The images released were impressive, with detail and resolution exceeding expectations, not just from the engineers and mission support specialists who have worked since Christmas of last year commissioning the telescope, but from all. It wasn't just the images. The images inspire, yes, but they also bespeak a detail contained in the data as deep as it is rich, a detail that was perhaps more impressive than the visceral wow of looking at an image whose resolution just gets better the deeper you look. Of the 5 studies released on July 12th, the SMACS, the SMACS 0723 Galaxy Cluster Study was probably the most content-rich of all. Of particular note was the long-distance spectroscopy of 4 high-redshift galaxies. Don't worry if some of these terms are unfamiliar. We'll describe them as we continue. Of the 5 instruments on Webb, we'll focus on those 2 that made this first of 5 studies released possible. NIRCam, the near-infrared camera that, as the name suggests, images objects of interest in the red part of the visible spectrum through what is known as the near-infrared, a region of the electromagnetic spectrum just beyond red. In short, infrared light is heat. NIRCam was designed to work with NIRSpec, a spectrograph that is capable of simultaneously recording the near-infrared spectrum of up to 100 objects such as stars and galaxies with low, medium, and high resolutions. What does this all mean? And what is a spectrograph? When we see a rainbow on the sky after heavy rain, we're seeing the result of millions of drops of water acting as tiny prisms, each breaking the sun's white light up into its component colors. A spectrograph acts in much the same way, breaking up the light from a distant source into its component colors, and recording that analysis as an image. We can thus determine the composition of an object of interest, be it a star, a nebula, a galaxy, and now, with NIRSpec, a cluster of galaxies, all at the same time. We can now determine the makeup of that faint, distant light that has been traveling for over 13 billion years. Light that left those galaxies long before the sun shone bright in space, not long after the primordial inflationary event, colloquially known as the Big Bang. We now have the capability of studying the composition and makeup of that nascent universe, the composition of the gas, stars, and makeup of those faint relics at the limit of detection. The James Webb Space Telescope has, quite literally, allowed us to look back in time and space to the beginnings of the universe. And this is where we begin now. We can unequivocally state that our evolutionary theories of the early universe have been confirmed. Using NIRSpec data, we will present compelling evidence contained in this data for this confirmation, data that was not discussed but yet was hiding in plain sight. We modify published NASA graphics highlighting spectroscopic features of iron already included but not highlighted or discussed by the authors. We comment on the relevance of these features coupled with the spectral features already highlighted to unequivocally show how heavy element nucleosynthesis was shaping the early universe. This is something that has long been postulated, but we now have clear and compelling evidence that it did in fact occur. In order to provide background and context, I need to briefly discuss the universe's beginning and early evolution. Ever since Georges Lemaitre proposed in his 1931 paper that the expanding universe began as a singularity, also known as the Big Bang, the view of ourselves and our universe has been forever altered. If you're watching this video, then you've probably heard of or read Steven Weinberg's The First 3 Minutes or Stephen Hawking's A Brief History of Time. So let's take a brief look at the chronology. After the first second, the expanding universe cooled such that protons and neutrons, the building blocks of matter, what we see today as matter, also known as baryons, nuclei, atomic nuclei, emerged from the expanding superhot plasma. After about 2 minutes, conditions allow nucleosynthesis to begin in open space. These are the conditions are superhot. One core of all protons and all neutrons fuse to form heavier nuclei. Initially, the products include deuterium nuclei, which consists of 1 proton and 1 neutron, followed then by mainly helium-4, would be known today as 2 protons, 2 neutrons. The plasma had cooled to about 1 billion Kelvin, hot enough for nuclear fusion to occur freely in open space. The primordial abundance. After about 20 minutes, the expanding plasma cooled below the point where nuclear fusion can occur. At this point, the primordial abundance was established at 75% hydrogen nuclei and 25% helium nuclei with trace amounts of lithium. This value established forever the total aggregate mass the universe will ever have. Since all heavier nuclei than hydrogen form as byproducts of nuclear fusion, all the matter that ever will be was created within that first 20 minutes as hydrogen and helium nuclei. In the 18-minute window between 2 minutes and 20 minutes, say this again, all the matter that will ever be was created in that time frame. From that point hence, the ratio of hydrogen to helium has slowly and inexorably decreased. As more stars form, free hydrogen, the raw materials for new star formation, decreases. The observed aggregate mass of the universe today contains 73% hydrogen, a value consistent with the Big Bang model. The Recombination epoch. The Recombination epoch begins at about 18,000 years as electrons combine with helium nuclei, also known as alpha particles, to form helium plus. After 100,000 years, neutral helium forms, and after 370,000 years, neutral hydrogen atoms, 1 proton and 1 electron, form, otherwise known as recombine. This is why they call it the recombination epoch. It's because these atoms recombine, right? As this epoch begins, the cooling plasma was still too hot to allow neutral atoms to form and thus existed as an opaque, ionized gas. The ionized gas was hot and opaque and thus no light could travel through it or out of it. This epoch concludes after 370,000 years with the formation of neutral hydrogen, 1 proton and 1 electron. At this point, the universe becomes transparent for the first time. The newly formed atoms, mostly hydrogen and helium with traces amount of lithium, quickly reach their ground state energy levels by releasing photons, massless particle of light. We know today that light has a wave-particle duality. Light can present both as a photon, which is a massless particle, and a wave. These photons are observed today as the cosmic microwave background, or the CMB for short. The cosmic dark ages and the first stars and galaxies. This epoch begins after recombination at 370,000 years and continues until the first stars form at about 400 million years. During this time, neutral hydrogen, the raw material for star formation, exists in abundance, but gravity is slow to act. Stars form as pockets of gas, contract, self-gravitating to form protostars, heating up as they contract. Once temperatures internally, in their cores, reach 10 million Kelvin, nuclear fusion begins and a star is born. This process was slow to start during this epoch, but picks up after 400 million years. The Stelliferous Era. With the formation of the first stars, the Stelliferous Era, the second of 6 ages of the universe, begins. It will continue until all possible stars have formed and the last of the red dwarfs ceases to shine. This point on the cosmological timeline is 10,000 times the current age of the universe, or 100 trillion years. I'll say that again. This point on the cosmological timeline is 10,000 times the current age of the universe, or 100 trillion years. That's a 1 followed by 14 zeros, or 1 times 10 to the 14th power, 100 trillion years. To make sense of this staggering time scale, time is scaled logarithmically. Thus, each cosmic decade is 10 times longer than the previous. Although the Sun formed late, its lifespan is approximately equal to the current age of the universe. It could live and die 10,000 times before the end of the Stelliferous Era. We've only just begun. As the first stars grow in number, gravity draws them together to form the first galaxies and large-scale structures of the early universe. It continues to expand and evolve over the intervening 13 billion years to the present day. And this is where our story begins. July 12th, 2022. We're going to make frequent reference to the term redshift. Redshift is the shift in the observed wavelength of light, or its color, emitted by a receding source, compared to its rest wavelength, or the wavelength, its color, of the light when it's at rest or stationary. Of the 5 studies presented on that day, the SMACS 0723 Galaxy Cluster Study was probably the most content-rich of all. Of particular note was the long-distance spectroscopy of 4 high-redshift galaxies. Spectroscopic studies of 4 high-Z or high-redshift galaxies, Z denotes redshift, illustrate why Webb is necessary to study the early universe. Without Webb, we would not be able to observe these galaxies or their spectra. Most visible light from these galaxies has been redshifted into the infrared because of these galaxies' tremendous recessional velocity, and this one in particular at 98% the speed of light. All visible aspects, all visible information that we get from this galaxy and galaxies at the same distance and to the limit of Webb's detection, all that light has been shifted into the infrared. We can't see them without the special capabilities of Webb, allowing us to observe the universe in the infrared. The visible part of the electromagnetic spectrum is very small, from 400 nanometers in the violet, the boundary with ultraviolet, to the red at 700 nanometers wavelength. Beyond the red is the infrared, and this is where Webb observes the universe, in the infrared. A nanometer is 1/billionth of 1 meter, or 1 million times smaller than a millimeter. Very, very small. Each chemical has a unique spectral signature, the same signature visible here on Earth and at 13 billion light years. This uniformity and constancy of nature allows us to study and accurately determine the chemical composition of an object of interest, no matter where we observe it, whether in the lab or at 13 billion light years. The visible hydrogen spectrum is very basic. Known as the Balmer series, it consists of a prominent red line at 656 nanometers wavelength, known as hydrogen alpha, a blue-green line at 486 nanometers wavelength, known as hydrogen beta, a 434 nanometer blue line, known as hydrogen gamma, and a 410 nanometer line in the violet, known as hydrogen delta. Some spectra included in the published graphic contain species of the element of interest in some state of ionization, meaning the particular element exists there, but is in a high-energy environment, such as what might exist in the aftermath of a supernova, an exploding star, for example. redshift. Four well-known emission lines in the visible spectrum are redshifted well into the infrared. In the first spectrum, from right to left, hydrogen alpha, red at 656 nanometers wavelength, two visible oxygen lines, 496 and 500 nanometer wavelength. This last line is the famous doubly ionized oxygen line, and hydrogen beta at 486 nanometers. Take particular note of how strong the doubly ionized oxygen line is. The strength of this line and others will play a central role in this presentation. This line is indicative of active stellar evolution in this galaxy, even at this very young age. The greater the redshift, the further into the infrared the lines are shifted. With the exception of the first two spectra illustrated here, hydrogen alpha, the first in the Balmer series, is redshifted off the scale. It's invisible. The redshift values range from 2.81 for the first galaxy at 11.3 billion light years to 8.5 for the last galaxy at 13.1 billion light years. With a Z, or redshift, of 2.81, the first galaxy is receding at 87% the speed of light. The last galaxy, the object of study, with a Z, or redshift, of 8.5, is receding at 98% the speed of light. And for convenience for the rest of this video, we'll refer to this galaxy, the object, the galaxy of interest, as Z 13.1. There are three stellar populations: Population 1 stars, stars that are just forming now; Population 2 stars, stars similar to the Sun in age; and Population 3 stars, the very first stars that formed. Population 3 stars. Much conjecture surrounds the makeup and stellar population of Population 3, the first stars. Were they ultra-high mass stars over 100 solar masses? How long did they live? What was the stellar diversity of the young universe? With the published data from the SMACS 0723 study, we may now be in a position to answer these questions. The only relics remaining from the early universe today would be small, subsolar mass stars that live much longer than the Sun, K&M class stars. Their low relative luminosity makes them difficult to first detect and then determine their metallicity. This has been known for a while and is nothing new. Stellar metallicity and supernovae. Metallicity is the ratio of trans-helium elements heavy than helium, to hydrogen compared to hydrogen. Presumably, the smaller this ratio, the older the star. How so? Population 3 stars would necessarily reflect the environment from which they formed. Thus, the stars that formed then would reflect the paucity of heavy elements in that environment. Elements heavier than hydrogen are produced in the cores of stars through nuclear fusion. With the exception of type 1a supernovae, most stars will forever retain the heavier element byproducts of nuclear fusion. Hence, the only way the interstellar medium, the ISM, is enriched with heavier elements is through supernovae, either type 1a or type 2 core collapse supernovae. As the principal nuclear fuel in a star, hydrogen, becomes depleted, the star dynamically transitions to using the byproduct of that process, helium, as the next source of fuel. For stars similar to our Sun, this evolutionary chain stops with the helium burning cycle, a cycle that produces carbon and oxygen. For higher mass stars, this process continues, producing much of what is on the periodic table of the elements through iron and nickel for the highest mass stars over 8 or 10 solar masses. These byproducts are stored in the core of the star and are used in a steady progression of heavier element burning cycles, ending with silicon for the highest mass stars. Each of these cycles is shorter and shorter in duration, with the last, the silicon burning cycle, lasting 24 hours. Core collapse supernovae are the end state for high mass stars. The last burning cycle, silicon, of a high mass star greater than 8 solar masses, or 8 times the mass of the Sun, produces isotopes of iron and nickel. When the star attempts to use these heavy metals as a new source of nuclear fuel, it implodes and rebounds off the degenerate core, violently destroying itself in a supernova. The interstellar medium is where all new stars form. Thus, the metallicity of the star is directly related to the abundance of heavy elements in the interstellar medium. Through further analysis of the SMACS 0723 NIRSpec data, we present clear and compelling evidence of active stellar evolution and heavy element production in the early universe. Our galaxy of interest, Z 13.1, has a redshift of 8.5 and is thus 13.1 billion light-years distant. It formed during the intervening 690 million years between 13.1 billion years, its distance right now 13.1 billion light-years, and the 13.79 billion year age of the universe. The graphic, modified from the original, shows the strong presence of iron, neutral and singly ionized. Why is this significant? As we stated before, iron and nickel are the byproducts of the last burning cycle of a high-mass star. In addition to the other elements included in the original graphic, oxygen and neon, there is only one way iron could appear in the Z13.1's spectrum: Type 2 core collapse supernovae. Supernovae is a Latin term. Supernovae is the plural of supernova. Type 1a supernovae are ruled out as there is insufficient time at this point in the evolution of the universe for white dwarfs to form. White dwarfs are the progenitor stars or the initial stars of a Type 1a supernova. In the case of solar mass stars, a white dwarf is the very end state in the star's evolution and is typically 10 plus billion years or so after birth. So thus there's not enough time for those white dwarfs to have formed. They would be the end state of stars like the sun that live typically 10 billion years. So at this point there's less than a billion years since the beginning of the universe and when we observe this galaxy. The presence of oxygen, neon, and iron in this spectrum indicates only one thing: active or recent Type 2 supernovae. As we said before, the only place these elements form is in the nuclear cauldrons of high-mass stars, and the only way that those materials make it to the interstellar medium is through supernovae. Further analysis also shows, and it's also something we mentioned previously, that some of these spectra originate from ionized species of these elements. In other words, they originated in a high-energy environment, such as the immediate aftermath of a supernova. How can we be so sure that these same spectral features are indicative of supernovae? This chart illustrates the spectra of a Type 2 supernova in a galaxy a bit closer to home. Many of these same spectral features are highlighted in our modified graphic. Note the iron line forest centered on the hydrogen beta line at 486 nanometers wavelength. This same iron line forest is also exhibited in our modified graphic from the JWST NIRSpec data. Why is this feature referred to as an iron line forest? Many iron lines very close together appear as a forest, as it were, all clustered together very close. In this graphic comparison of bright line emission spectra, we clearly see the iron line forest close to the same respective location of the hydrogen beta line. Note the iron line forest in the blue-green portion of the iron spectrum. Note also the double oxygen line in the blue. These same features are represented in our modified graphic of JWST's NIRSpec data. The hydrogen beta line is the prominent blue line in the hydrogen spectrum, with hydrogen alpha, the red line, to the right. Implications and conclusions. The only way heavy elements are produced is in the cores of high-mass stars and Type 1a supernovae. And we've already concluded that Type 1a supernovae could not have contributed, since no white dwarf progenitor stars would have existed at this point on the cosmological timeline. And the only way those elements make it to the interstellar medium, and thus to the next generation of stars, is through supernovae. We have clearly shown this process to be occurring in the early universe. Here we have presented clear and compelling evidence of active stellar evolution and heavy element nucleosynthesis 690 million years after the Big Bang. Remember, it took 400 million years for the first stars to begin forming 13.39 billion years ago. At 690 million years after the Big Bang, there is compelling evidence of active stellar evolution and heavy element nucleosynthesis. Are we to believe that the first stars formed, galaxies coalesced from them, and the nucleosynthesis of heavy elements ongoing after only 690 million years? That leaves only 290 million years for galaxy formation. If this is accurate, then the universe was evolving and changing rapidly, as has been postulated. The only way heavy elements are produced is in the cores of high-mass O and B type stars and type 1a supernovae. These high-mass stars live no more than a few tens of millions of years. For example, a 25 solar mass star lives less than 10 million years before ending spectacularly as a type 2 supernova. It has been speculated that these early stars were massive, between 100 and 300 solar masses. While there is a theoretical upper limit to stellar mass, there remains considerable uncertainty. So, for now, this will have to remain an open question. 690 million years may sound like a long time. On cosmological timescales, it is merely the wink of an eye. Remember how long the stelliferous era will last? 10,000 times the current age of the universe? Our own Milky Way galaxy rotates once in 230 million years, rotating exactly 3 times during this interval. Recall, our galaxy of interest, Z 13.1, is the most distant of the 4 at 13.1 billion light-years. Considering the morphological characteristics of all 4 galaxies, i.e. their shapes, they all appear irregular with no apparent structure compared to the beautiful spiral galaxies we're all used to seeing much closer to home and much younger. Take, for example, the great galaxy in Andromeda, Messier 31, or the grand design spiral, Messier 81. The analysis presented in this video and in our accompanying article also allows us to more accurately constrain the timelines of the universe's early formative epochs. We see strong heavy element representation within a few 100 million years of the first stars forming. This result is remarkable and consistent with studies concluding that star formation proceeded rapidly. Some studies also proposed ultra-high mass stars living short, punctuated lives of 1 to 3 million years that rapidly enriched the interstellar medium. As stated, the prevalence and possible contributions of these ultra-high mass stars in the early universe remains an open question. Perhaps with the James Webb Space Telescope, we'll get more new answers than new questions. This video is the companion to our full-featured article in Astronomy for Change. Link in the comments section below.
This is Dr. Jim Daly of Astronomy for Change. May you come to love the stars too fondly to be fearful of the night. And remember, the Earth is a mote of dust floating in a sunbeam. That's reality. Everything else is just marketing. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect a positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized.
If you enjoyed this video or found it educational or useful, please consider subscribing to our YouTube channel and sharing the video. These actions on your part are free to do and will help us grow. Also, why not consider supporting us by leaving us a tip or buying us a coffee or perhaps visiting our Patreon page? Any amount would help and would be most appreciated. All the links and details are in the comments section below. And, as always, thanks for watching.